So we're talking about CORTECONs, standing for Content-Retentive Temporally-Connected Neural Networks. They're the latest, greatest, newest thing in artificial intelligence. They're a new class of neural network. Welcome in, I'm Aliana Moren from Themesis. So do you remember reading that Philip K. Dick novel on, it was Do Androids Dream of Electric Sheep? And it was 1968. I know that because I looked it up last night. So androids and dreaming, and it posed a plot about very realistic, human-like, almost undetectable androids. And it was a plot line totally worthy of in fact, better, maybe a good deal bit better than some of the current movies that are showing up on our silver screen or our little laptops. So this poses the question, what's it going to be like as we realistically approach some sort of artificial general intelligence? And the question has been raised, we all know, about are we getting some sort of real intelligence within large language models, LLMs? And of course we know we're not. Of course we know that. But certain people still seem to think that that's the path. Okay. We know we don't need to go down that road too much further. Autoregressive engines. Look, we're not going to get AGI, artificial general intelligence, out of the basics, the things that we already have, that we know, that we love. Anything that is a Boltzmann machine derivative, we know what they can do. So there's nothing new there. Nothing that's going to come out of CNNs, nothing that's going to come out of the autoregressive algorithm behind LLMs. Reinforcement learning, pretty boxed and bounded, working on it, but it's still a fairly boxed and bounded, not a very generalizable type of thing. Variational inference, now that has possibilities. But by itself, it needs a little something, and that's what we're talking about today, CORTECONs. Now, CORTECONs are a kind of neural network. Let me take you back, though, a couple of moments in time. The time is 1986. 83 through 86. We've got the Boltzmann machine. Smolensky, 1986, suggests changing the architecture of a Boltzmann machine to make it more multi-layer perceptron-like. This is a profound moment. What we did at that moment, and this influenced our thinking here ever after, so we want to trace our origin story here. We removed all the connections between the visible to visible nodes, and visible includes both the input and the output nodes if we're trying to cast this into an MLP, multi-layer perceptron framework. And we removed the connections between the hidden nodes, the latent nodes. They couldn't talk to each other. It was all strictly visible to hidden, hidden to visible. It was a moment. And it gave a certain kind of conceptual clarity. It allowed great breakthroughs, obviously. We've built up so much since then. But it was a defining moment, because all of a sudden you didn't have crosstalk. So imagine that you're in an office with people and you're not allowed to talk to the person at the neighboring desk. And heaven forbid that there should be an office party with birthday cake, just not allowed. You've all got to be very task focused. You take in your inputs, you process it, you send it onward. That's what our neural networks are like. No crosstalk. So be as it may, let's move on. In that same time frame, I think it was 1989, Gorman and Sejnowski, the initial experiments on how large should our hidden layers be. And that was a tremendously important moment, because we started to play with that whole notion of creating hidden layers that could optimally address certain tasks. So what we did at that time was define the road that was predominantly traveled. And today we're talking about the road less traveled. We're going back to that notion of the latent variable layer. We have to, in a recent vid, and all the links are going to be not in the description box below. Go to the description box for the link to the blog post. From the blog post, go to the links to the related vids. So in this vid, we were identifying the key themes or the key concepts that showed up in all the major neural networks and machine learning methods. Latent variables key throughout. So we'd obtained latent variables then, and we were experimenting with really reducing down that latent variable layer size to the optimal necessary. Today, let's think about something different. Let's say that we can have a relatively large latent layer. So I'm going to ask you to imagine, sort of just for now, just for fun, say a 16 by 16. This is still toy, latent layer. And new to us with this method, never in any of the previous methods, imagine that we've got this latent layer arranged as a spatial grid. Just do the usual checkerboard thing in your mind, and then offset every other row by a little bit. So you get a chessboard or checkerboard where the rows are slightly staggered. That's going to help us compute different kinds of local variables, nearest neighbors, next nearest neighbors, triplets, all essential for what we're doing. So we've got these local variables, and you can have potentially communication between them. We're not worrying about that mechanism right now. What we're going to do is back our way into the entropy equation. The unique thing about a CORTECON is that we're going to minimize the free energy across this latent layer. Now when we do that, well, we had a little moment last night. I shot the vid that you just saw in the setting sun of the beautiful Hawaii evening. And as it turns out, in the tropical area, even the setting sun is a bit too bright. It hit my face and everything all of a sudden went white. So here we are resuming with just a voiceover this morning. So here we are taking a look at the free energy equation for a one-dimensional grid. What you saw in the previous slide was a depiction of a 2D grid, and of course you want to go there because that's where the interesting topologies are. But computationally, we're going to play with a 1D CVM, that's cluster variation method grid first, until we're very comfortable with it. We can turn it upside down, move it sideways, and make it do all sorts of tricks, and then we'll progress to the 2D where the real fun happens. So just take a moment with me and take a look at a couple of features in this equation. The free energy, and we're dealing with a reduced free energy here, which means that we've divided through by a temperature term. So the free energy is a reduced enthalpy minus the entropy. The enthalpy is an expression of the energy associated first with the activation of different nodes, and second with the interaction between those nodes. The entropy deals with the distribution of data amongst all possible states in which that data can exist. Now let's take this understanding into that equation for the one-dimensional cluster variation method. Now the first term in this equation, the one that has epsilon multiplying a sum of z's, that's a enthalpy term. In this particular version, the enthalpy associated with having a unit on as opposed to off, that's called the activation enthalpy. That one's set to 0, so we're not even seeing that term here. What we're seeing are interaction enthalpies. Even though this is expressed in terms of z variables, which are triplets, what it really represents is interactions between nearest neighbors, and that's very similar to what we see in all the Ising models that are the simplest form of a free energy equation in statistical mechanics. So that one's very straightforward. The next two terms, where you see sums, those are sums first of the nearest neighbors, those are the y's, and the triplets, those are the z's, and there are some multiplying factors in there. Together, these two terms give us the entropy for the cluster variation method in one dimension. The remaining terms are Lagrange multipliers. Those are devices that help us solve this equation analytically. They'll pretty much come out in the wash as we move towards a solution. So what we see, fundamentally, is enthalpy minus entropy. That's the standard. It's very much the same that we've seen in all other simple, straightforward free energy equations. The difference is that for the first time, the interaction between yourself as a node in this grid and your nearest neighbor and your next nearest neighbor and your triplet, which is a combination of nearest neighbor and next nearest neighbor, actually count. Those interactions, not the energy thereof, just the physical placement of it. Are you near a like node or an unlike node? That actually makes a difference in the overall free energy. Radically new and different from what we're typically used to. Not that the equation is that new. The equation was developed, 1951 by Roichi Kikuchi. Further evolutions in 1967, Kikuchi and Brush. So the equation's been around. It hasn't been popular, but it's been around. So we're going to play with this 1D version for a bit. We're writing code. If you caught the last video, that was the first step in a code walkthrough. We were figuring out how to denote. It wasn't calculate, it was doing a denotation of the next nearest neighbor to our immediate left, where we, in this instance, are a node within the grid. We'll complete this we'll have a lot more code walkthroughs, but let's pull our attention up a level and get back to the overall topic of discussion. We're talking about a grid of latent nodes, and we can minimize the free energy across that, and that allows us to do things, because once you minimize the free energy, and let's suppose that the on nodes are on both because of random perturbations, or a certain fraction of nodes simply have to be on to hit a free energy minimum, but also we can introduce this latent layer into a traditional neural network architecture, and then the activations of some of these nodes can be functions of the input and the latent to the output node activations, very much as you do in a typical MLP or even a restricted Boltzmann machine. Now, the reason for this is that when you remove the input activations, the activations within the latent layer don't all just go to zero. Instead, because you want a free energy minimum here, you're going to have to keep some nodes in an active state. And you can persist some nodes in an active state. We can introduce functions for degrading activation over time. And we can have crosstalk between latent nodes that allow nearest neighbors to encourage each other to stay active. There are other things that we can introduce. That's just a summary of highlights. It's so good to be back. This is a second video shoot. Same costume, same environment, different day. Now, we wanted to pick up with where the video editing left off the last time, which was doing a voiceover, and I believe that we left off with some descriptions of the equation itself. So let's back our way up. We have 3 topics to discuss to wrap up this vid. Number 1 is wrapping up the equations in the architecture, which we'll do very briefly. Second, we want to touch briefly on CORTECONs and AGI, or artificial general intelligence. We want to show how those two will likely intersect at some point in the fairly near future. And third, we want to talk a little bit about intellectual property, shall we call it reproductive rights, meaning can you use this material yourself? And if so, what are the consequences? So let's do that third one first, okay? Just get that out of the way. We've invented this. More specifically, I've invented this. And I created, as founder, the company, Themesis, as essentially an intellectual cup in which to hold these inventions. So we're inventing this, the CORTECONs, and actually it's a 30-plus-year-old invention. I did the very first work back in the 1992 time frame. There's a few papers there, conference papers. That just establishes an ancestry, so to speak. We'll do a little bit of backstory later. We'll discuss, for example, where did the notion for creating CORTECONs come about? How did I come across this particular free energy equation? And, spoiler alert, I did my PhD on it way back in the mists of time. I essentially had this in my hip pocket as I transitioned into early stage neural networks. We're talking the 1980s and early 1990s time frame. And I was in a particularly fertile, creative, juicy environment that fostered the kind of thinking that led to the CORTECON. Again, that's a story for another day. The point is, because I'm transferring my personal inventions into Themesis via a corporate agreement, so Themesis owns this material, we are making large elements of this available to you under the MIT license, so by all means, feel free to go and get that code and use it, play, have fun. This is all very new for most of us. A CORTECON, a basic CORTECON, consists of a neural network. Envision a multi-layer perceptron, and by the way, we should probably be running CORTECONs in a side-by-side with a traditional neural network. So imagine a traditional multi-layer perceptron over here and a CORTECON there, and use all the traditional training methods, your choice, to get these vertical weights going on. And for the CORTECON itself, once you've got weights trained, you can train directly from input into the CORTECON into an output, or you can train from a learned latent set of representation nodes into the CORTECON into, for all that we care, another latent set. It doesn't really matter. We're talking about a general architectural framework, and less trying to tighten things down. Remember that a CORTECON is a general architectural class. I'm expecting a huge number of various evolutionary expressions on this theme over the next few years. Now, within the CORTECON, we have that latent layer that undergoes a free energy minimization. This is not the same kind of free energy minimization that we have in the traditional energy-based neural network, where you are adapting every single individual connection weight. Now that's with a Boltzmann machine. In the CORTECON, you aren't adapting individual connection weights. There's a different kind that you can adapt, but we're not discussing those at the moment. Instead, there are only two parameters, epsilon 0, epsilon 1. For a lot of the research that we'll show you over these next several weeks, it'll be epsilon 0 set to 0 because there's an analytic solution and we can compare what we do computationally against the analytic. That's just a happier place for everybody until we're all very safe and grounded. That's another training wheel step. What you do when you have these epsilon 0, epsilon 1 parameters is you control the clustering behavior. Specifically, epsilon 0 controls the relative fraction of nodes that are on. So slidey scale on epsilon 0, you can make it relatively few on nodes versus up to 50%, even more. Most of the time you're going to want slightly less than 50% because you don't want the clusters to overlap each other that much. Okay. Epsilon 1, a different parameter, slidey scale, controls your clustering. Do you get great big massive clusters? Are you sort of forcing things into continent-sized masses? Or are you getting lots of individual little islands that happen to connect with each other? There's a lot of little connection things in the topologies. You're not really going to control which specific nodes are on or off with these epsilon 0, epsilon 1. That will be some actual connection weight training. That's why we still have the inputs from your input or a latent layer into the CORTECON layer and then out. That's where we do the training to establish initial activation of nodes. But then the beauty is you stop that initial activation and you can get that range of interesting behaviors. We'll discuss interesting behaviors some other time. Right now we're just going to give this a rest and say that the primary engine is this free energy minimization across the latent layer that allows interesting behaviors to emerge. We can of course have other factors such as activation decay and internode communications or connections. We can, for different evolutionary versions of a CORTECON, modulate these with different functions. Enough said there. That'll carry us for the moment. So here we are. CORTECONs, artificial general intelligence. What's going on? First of all, we want to identify the core element of the CORTECON, which is that free energy equation and its couple parameters, epsilon 0, epsilon 1. With that alone, without getting fancy, no input-output layers, no interactions across the latent layers, nothing except some really basic, simple two-parameter physics. You can model a lot of different kinds of topologies. So if you are trying to model the essence of a two-state system, a bistate system, that can be represented in a two-dimensional grid, then the CORTECON is the perfect tool. And we're not even talking a full CORTECON, just the internal engine. Now this is the kind of thing that's perfect if you're modeling, for example, a change in terrain. You're going from urban or suburban to rural. If you're going from, say, deciduous trees to pine trees. Any kind of shift in the natural topology that can be represented as bistate. You can be a little bit more abstract. You can be talking about whether it's friendly or foe forces in a two-dimensional space. Now, unless you're doing the activation inputs and the outputs that stabilize activations in certain nodes, you're not going to get specific nodes to represent specific elements in the corresponding natural terrain. What you're going to get, and this is important, what you're going to get with this kind of a CORTECON is the data that we are representing close to equilibrium. So you've got the actual data, the field around yourself, that's called psi by Carl Christen in his papers. You've got the representation of the data, which is how you chop it up and put it into some sort of grid with on-off nodes that you are going to then apply the CORTECON engine to. And you've got the model of the representation, and the model is subject to just two parameters. So The first question that we can be asking is, are we close to equilibrium? That is such a powerful question. To the best of my knowledge, there's only two works in existence where the 2D cluster variation method has been used to model two-dimensional topologies. One is 2021 work by Noor Sajid and Laura Convertino, advised by Carl Friston, and they use the CVM to model cancer niches. And then the second work is that I've developed a variational approach to identifying the parameters that bring a CVM grid, the 2D CVM model, into greatest alignment with the actual representation. And I'll put links to both of those papers in the blog post. One little note, that work on variational parameter estimation for the cluster variation method is something that's absolutely essential to making it work as a good modeling tool. I just got that work done less than 2 years ago, which is why there's probably not been many published works using the cluster variation method to model topology. The important thing about this is almost all terrains that you would model in any respect, are they natural or are you doing some sort of representation of an abstract thing like friendly or non-friendly forces? The important thing is not only are we close to equilibrium, but what do we have to do to these parameters to bring this model of the system towards equilibrium? So that would be turning a few things on and off. Adjusting the model grid, you can't really adjust the representation because it is what it is. It's representing external reality. But you can adjust the model to bring the model to equilibrium for different pairs of these epsilon values. And you can find the closest matching pair of epsilons, and that tells you a little bit about the space in which this actual external system really exists. Now, if you're in a space where we're getting close to AGI here, in a space where the nature of the actual data is changing and therefore the representation is changing over time, then the model for the representation would also change over time. And then the question is, do we have some sort of trajectory through a phase space, and can we predict where the next blob in this phase space might be? For example, if we are in a system that has massive clusters of on nodes in sort of a sea of off, and we've got a few little islands of on nodes, or we've got these little fine spider legs connecting masses of on nodes. If we start there, are we migrating towards something that is more splintered, more fractured, or vice versa? Can we predict a logical course of action? We may not be predicting exactly which nodes are going to flip on or off. We could predict the overall nature of the evolution. That's something right there, never been done before. Okay? Now, when it comes to the AGI, let's talk variational inference, and from there let's just quick step to Carl Friston's work with active inference. And there's some interesting work done by Hafner et al. In a group that included Friston and a number of other peers that he publishes with a very interesting paper. I will of course link to it in the blog post. The important thing is there's a potential step beyond active inference, which I'm just going to ask you to check out that paper if it interests you. What we're dealing with is a form of variational inference in which we are dealing with a Markov blanket, that is, something separates our model of the system from the actual system itself. And in that case, what we're dealing with a CORTECON employed there is that the CORTECON becomes the model within this variational inference structure that is separated, where the representation is separated from external reality via some sort of observational and action boundary. Here's what's important about that. The model itself can be brought to free energy minimum. That is so radically new. It's hugely different. Typically, when you look at variational inference, the model that is trotted out for everybody's perusal is something like families of exponential equations. Those are extremely popular because they are so well known, so well loved, so predictable and understandable. If we're going to use a collection of Gaussians, we're just saying, just for an example, then the question becomes, how many sets of Gaussians do you want? And then you have the parameters for each. That's a pretty well-known model that we can use. But there has never before been a model where the model itself can be brought to free energy minimum. And then you can assess, oh my, how far is the actual representation from this free energy minimum? What would we have to do to the represented data to bring it closer to the model that is at a real free energy minimum? What is the fact that the representation has elements that are not at free energy minimum? What can that tell us? In other words, if there's a massy area of, say, a large element of all on, and then we've got a lot of splintered, fractured little off elements, and then maybe an all on, so it's not really fitting into a given set of epsilon parameters, what is that telling us about our system? These are questions that we can ask, and if we can predict how the system is evolving, then we have something that has never been done before. We can say, as the system is represented by something that is brought to equilibrium, then if we move through an equilibrium trajectory, this is how it would unfold. Brand new toy. We'll have so much fun with this. We're going to have a great time. So, once again, I'm Aliana Moren from Themesis. Please go to the blog post. The blog post will not only take you to the various papers that we've mentioned, but also to the GitHub repository where there is code. We invite you to use it. This is all 1D code. It's in its infancy at the moment because we are transitioning the code that we've already written that is basic structured Python. We are writing new code. We're taking that two-dimensional cluster variation method code, CVM for short, okay? And we are writing a object-oriented approach to the same thing, starting with the one-dimensional CVM, and that's going to be freely available to everybody. Then we'll be releasing 2D CVM, probably within the confines of a short course, because we want to take people in a very steady, graded manner through the material and not have people just sort of randomly grabbing things off YouTube and then emailing us saying, oh my goodness, what's this? We'd rather bring you through this in a stable manner. If you want further connection with Themesis on the subject of CORTECONs, we'd be delighted to work with you. We are a muse. That means that Themesis is not a basic consultant. We're not a coach. We're a muse. The difference between a muse and a mentor or coach is that a mentor will evolve you into the path that they used, and then you become the best replica of who they are that they can bring you to be. Think of Obi-Wan Kenobi and Yoda in Star Wars. Think of the older Zorro bringing the younger Zorro in The Return of Zorro into being the new Zorro that emerges to right wrongs. We recognize that you have your own agendas to explore, and we act as a muse to encourage your evolution in the paths that you want to go into. So if you go to the Themesis website, you'll find a menu item that says Muse. Click there. You will also find something that says Protocols, and check that out because we have a very structured means of communicating with people who would be our future clients. Thank you. It's been so lovely to have a moment with you. We look forward to visiting with you again soon. Have a lovely day.